All right. I would like to inform you where your student fees went. I spent most of them on equipment. These are influence line generators. Ladies, please take a pink one and pass it down from the carrier case. Guy's getting ready to get hit in the head. He's totally oblivious. Pass the spares back to the section that didn't pay their fees, please. Got some left over? Any you have left over, just pass them back. These are not cheap. They're very expensive. They're very special. You will be expected not to lose them. Did you get yours? No? Well, you just lost out. They sell them for $20 in the student services room. If you'd come on time, you'd know. Please put your name on it now. How many influence line generators are still in that case? Give me one of them. Thank you, sir. All right. A short review of what we're doing and why. Here's a typical beam. No, sir. No. Just this piece here. Sorry. Thank you. A typical beam, it is 20 feet long, simply supported on each end. I have shown you a couple of special points, the ends and at the 5-foot marks. If you were to draw an influence line for the shear at C, probably because you have a splice in the beam or something like that at this point, and you want to know how to design that splice, and you've been told by the boss you need to know how much shear the worst case for the shear at point C is, then you would draw me a shear influence line to let me know where to put the loads to get the worst case shear. Now, this is not the worst case shear. You already know from your pop quiz, because it seemed like everybody did that right. For the worst case, you would put the load right wherever the influence line is the maximum. But if I asked you for the shear at C due to a 20 kip due to a 20 kip load at B, here's how you would tell me what the answer was. And I'm looking for a more general answer than just the max in this case. You would draw the influence line, which would tell me the influence on the shear at C for any unit load position along the beam. You would tell me if you put the unit load here, there would be no shear at C. You could put a unit load at the 5-foot mark. You'd solve for the reactions. You'd cut the beam and solve for the shear at C. And you would plot the resulting answer at the point where you put the unit load. Then you could move it in the middle. Then shears, you always have to do two of them because there's an answer to the left and an answer to the right of the shear. and you'd put a load there, and you'd put a load there, and you'd again solve for the numbers, and you'd plot them. Then when I came in and said, all right, on this exam, you can bring anything you want. I'm going to put the load somewhere on the beam, and I'm going to ask you for how much shear is caused at point B. If you were smart, you'd draw an influence line so you'd have all the answers ready to go. And your answer would be, you know the height of this is 0.75. We'll do more of these so you'll see that that is the right answer for this influence line. And you would come over to the 5-foot mark, which is a third of the distance to this number, and you'd say that the height of this is a third of 0.75. And you would multiply the 20 kip load, and you'd multiply it times 0.25, and that would be your answer. That would be the answer for the shear caused at B due to a 20 kip load the shear at C due to a 20 kip load located at B. So what, a quarter of 20 would be 5 kips. Incidentally, these shear influence lines, boy, there's a gaffe. They are not shear diagrams. They may look a lot like shear diagrams, but they're not. The influence line for shear has no units. Let me see if I can explain why that is. Because I don't want it to have any units. In other words, well, I don't know a much better way to say it than that. You'll notice that when you multiply load times my influence line, your answer is supposed to come out in kips. And your load has the units of kips. And so the truth is, I'm not going to let you put a 1 kip, 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 because then these things here would have the units of kips. I'm going to ask you to generate your influence lines with a 1, a 1, a 1, a 1, with no units, thereby causing a reaction which has no units, which causes an unbalanced shear inside the beam with no units, which causes an influence line for shear with no units. Then when you multiply your load times the height of my influence line, your kips times my nothing gives me the right units. Now that's basically what we've been doing. We've been generating influence lines, and basically we really will use them in this fashion. We will, first place it tells you where to put the load. And if that's the only load, we already know where you'd put it. To get the biggest positive shear, you'd put it just to the left of point C. To get the largest negative shear, you'd put it just to the right of point C. Now, the beam that you and I have been working with in the past, I have forgotten what it looks like because we've got one thing left to do on it. You and I have generated influence lines for reactions. We have generated influence lines for shear. And now then I want to generate an influence line for moment. Here is the stuff from last time. The influence lines that we generated were for a 12-foot long simply supported beam. We moved the load to the 0, little bit plus to the right of the reaction. We moved the load to the 3-foot mark. We moved the load to the 6-foot mark. We moved the load to the 9-foot mark. And then we just figured out that if you move the load all the way to the right, and we plotted the reactions, the influence line for the reaction at A, the influence line for the reaction at B. Then we came in and we did the same thing for shear. We had a 12-foot beam. I don't know, this is probably where the unit load started. Here's where it ended up right on the reaction, causing nothing. Then we moved it a little bit to the right. We drew a free body of the section that was generated, and we solved for the shear, and we plotted that shear. And all of those K's now I'm going to ask you to remove. Back when you were babies and couldn't take it, you know, that if it was a 1, it had to be a kip, or at least a Newton. Now then, this guy's going to have just a 1. He'll have no units. And therefore, the influence line, this is the influence line for the shear at A, just a little bit to the right, and you'll notice it really has no units. It's not supposed to. Now I'm going to do the same thing exactly for bending moments. Here were our free bodies. So let's start with these. This was 3 feet. This was 0 feet. This was 3 feet. This was cut over here 6 feet. I don't know how many of these things we got, because it looks like I got another one here 6 feet. I don't know. I'm not going to try and reconstruct that. Let's just do another one. It's a 12-foot long beam. Here's a 12-foot long beam. Here's the left reaction. Here's the right reaction. I am going to generate an influence line for the bending moment. This is point A. Let's just pick a point right here, 9 feet over. I'll call that point B. Here's point C. So I've asked you to generate an influence line for the moment at the 9-foot mark. First thing that I'll do is I'll draw you a beam with a unit load on it. Whoops, that's old hat. I'll solve for the reactions. I will cut the beam at the 9-foot mark, and I'll draw you a free body of either end. Here's the free body of the left end, just to make sure everybody really agrees that we're going to get the same answer regardless of which end we cut off. This is a reaction of 1. There is your unit load of 1. You'll notice it looks very slightly to the right, but that's just a figment of your imagination. It's pretty much right over the reaction. This is 9 feet. Here's the moment inside of the beam. I'm going to show the bending moment as a positive bending moment inside the beam. You need to remember that these are positive shears, and these are positive moments inside the beam. This is the moment at the 9-foot mark. Solving for the moment at the 9-foot mark, 1 times 9 minus 1 times 9. The moment at the 9-foot mark is now 0. So the moment at the 9-foot mark is equal to 0 for this case, for the load being here. We'll come back and pick these up and plot them. Next, first let me do the other end. Here's the other end. The load, I don't see it because it's down here on this end that's missing. Here is a positive moment shown on the beam. You'll notice that if you cut this end off, the moment should be shown that way to call it a positive. If you cut this end off, you should show the moment in the beam in that direction. And this moment is that moment. They both agree in sign. Someone who's acting counterclockwise on this piece of steel will have this guy acting clockwise on the other piece of steel, the other way. Here's his reaction. His reaction was 0. He is 3 feet away. And therefore, the moment here is 0 times 3. That's the same thing we get here. That agrees. So now you can cut off either piece you want. I'm just going to, for the heck of it, go ahead and cut off the left end. Here's my new position of the load. The position of the load is now 3 feet from the end. You have been asked to generate an influence line for the shear at the middle, at the 9-foot mark. So I'm going to come over here and I'm going to cut it at the 9-foot mark. With this load, there's your reaction, and there's your reaction. By now, I don't think there's anybody can't solve for reaction, so I'm not going to bother doing it. Here is the free body. Heck, I'm going to cut off this end. That looks like the easy end. There's the free body. There's the reaction. Here's the cut face. There's that 3 feet. Here's a positive moment shown on the beam. This is the moment at the 9-foot mark under the new conditions. And the moment at the 9-foot mark under the new conditions is 0.25 times 3, 0.75. And what are the units of this 0.75? Now you may think they're 0, but they're really not. When you put a 1, a unit load on here, it has no units. It caused a reaction of 0.25 with no units. When you multiplied your 0.25 with no units times 3 feet, it turns out the units of an influence line for a moment, they're feet. Next, I'm going to draw you a beam. I'm going to put the load in the middle. That's 6 feet and 6 feet. Here's where we're going to cut the beam to find the answer. 3 feet over. With the load in the middle, you get 0.5 and 0.5 with no units. Here's the free body of the piece of beam. It's 3 feet long. It's cut right here. It has 0.5 for the load. Here's your internal moment because you put a unit load in the middle of the beam. M at the 9-foot mark now is equal to 0.5 times 3 is a positive 1.5 feet. I'll certainly admit the units look weird, but then these are not moment diagrams and they're not shear diagrams. If you got any questions, you need to holler. If you say, I don't see how anybody could have a question, that's good too. Next, I draw you a beam. 12 feet long. I'm going to put the load. Now, if you remember, the shear diagram had a kink in it when it went over the point we were looking for the influence line. So what I'm going to do is I'm going to put this over here 9 feet minus, just barely to the left of point B, where we've been looking for the answers. Yes, sir. Why did I? Well, I didn't cut it at 6 feet. Why did I not? I did not cut it at 6 feet because my boss didn't ask me for the influence line for 6 feet. See, I always cut the beam and find the answer inside the beam at the point the guy wants the influence line. So that's why even though the load was here, I cut it 3 feet back. Even when I move the load, I cut it 3 feet back. Even when I move the load to the midpoint, I cut it 3 feet back. And now then that the load is pretty close to the point you're looking for the influence line for a moment, it's a little to the left, I'm still going to cut the beam 3 feet back. The reactions now will be 0.25 and 0.75. Here's the free body of the little piece of beam that's 3 feet long. It now has a reaction on this end. I haven't been saying R, so let me just put the number as 0.75. Here's the moment caused by the load inside the beam at point B. There's the moment at the 9-foot mark is equal to 0.75 times 3. 75 times 3, 150, 225, is that right? 2.25, and it has the units of feet. Now this is statics. This is what I told you. This is the way you can always get the answer. I mean, it's long and slow and laborious, and there's no question about it. There's only one reason to pay $20 a piece for those influence line generators I gave you, and that's if it does it quicker and easier and nicer and all that kind of stuff. But sometimes you'll find those things don't work too well. Next, I'm going to draw you the same beam, but instead of moving the unit load slightly to the left of point B, I'm going to move it slightly to the right. So this is 1.0. This is 9 feet plus. The beam is going to be cut at 3 feet, which will be just a little to the left of the load. Now the load shows up inside the moment inside of the free body. Here's what the thing looks like. The load only moved over 1/trillionth of a micrometer, so the reaction here stayed at 0.25. It went to 0.25000001, and this one stayed at 0.75. Here's the free body. 0.75. Here's the cut face. There's the length of the beam. Here is the internal moment generated. That's the moment at the 9-foot mark. And you also see the load 1.0. When I now sum moments about the cut face, the moment at the 9-foot mark for this location of the unit load is 0.75 times 3 minus 1 times 0. It's still the same number as before. So there isn't a kink. Well, excuse me. There is a kink. It'll have a discontinuity. Its slope will change from one direction to another direction, but it isn't a jump like in a shear diagram. The value is the same. It's just the slope will be different on the other side. So that's 2.25. This is 0.75 times 3 feet. So the units of an influence line for moment are feet. Now, I don't know. I could go all the way to the end, but that's a little dangerous. I'm not sure I'm willing to do that. So I'm now going to move the load over to the 1.5 foot mark. So this would be 12, 11, this would be 10.5 feet. I am still going to cut the beam at the 3-foot mark. Because that's where I always cut it, because that's where I've asked you for the moment influence line. Somebody got a calculator? There you go. I see. Is that a calculator hanging out? Oh, that's for texting, huh? Wonderful. Thank you. 0.875 for this reaction right here. And therefore, the reaction on this side would be 0.125. Is that right? Whatever's left. Questions, anybody so far? Okay, and this is a 1. Now here's your free body. There, it cut it at the 3-foot mark. Here's your reaction, 0.875. Here is your load, 1.5. The load was 1.5. Here is the moment. Incidentally, there was a shear inside here too, obviously. Since I kept some moments about the cut face, I didn't have to solve for it because it had no moment arms. Incidentally, that shear, that's the same shear that we got back here when we were doing all these other things, when we were solving for these shears last class. And this is the moment of the 9-foot mark. I'm going to go ahead and solve for that one. Sum of the moments about the cut face is equal to 0 is equal to 0.875 times his moment arm is 3 feet. That's a plus. Minus 1.0 times his moment arm of 1.5 minus m sub 9 foot. Move that to the other side. M sub 9 foot is equal to, thank you, sir, 1.125. Does it come out a plus? Yes, it does, doesn't it? Because this times 1.5 is 1.5, and that is smaller. No, this is the winner. This is the big number. But that's okay, because m sub a goes on the other side as a plus, so the plus, that's a positive answer. You got a calculator, you know, you can tell. And the units again are feet. Now, this is where the rubber hits the road. This is where I plot the influence line for the moment at the 3-foot mark on this beam. First, I draw the beam. I have answers here. 1, 2, 3, 4. I have answers in the middle. 1, 2, 3, 4. I have answers on the end. Halfway out, I have answers. A little to the left, I have answers. A little to the right, I have answers. That's where I'm going to plot the numbers. The answer for the moment at B with the unit load at this location is to be plotted at this location on the left end. The answer was 0. Don't know how that didn't get written down. 0. When you move the load to the 3-foot position on the beam, it caused a moment at B. The moment it caused at this point, the magnitude is to be plotted where you put the unit load. That's so later on when you come in here with a 20-kip load and you want to put it at the 3-foot mark, I know what to multiply it by. I'll multiply it times the ordinate that you have plotted. The answer to be plotted is 0.75. There's 0.75. When you move the load to the 6-foot mark, you caused a moment at this point. The magnitude of the moment that you caused at this point is to be plotted where the load was placed. So when you come in with a 60-kip wheel load in the middle, I'll know what to multiply it by. It is to be multiplied times the ordinate of 1.5. Here is 1.5. Looky here. When you move the load to the 9-foot mark, it caused a moment a little to the right of the 9-foot mark, 2.25. 1, 2, 2.25. You know what? Somebody that said influence lines for statically determinate structures are straight lines. It looks like they are indeed. Now then, we have an answer just a little to the right of that, 2.25. The answer a little to the right of that was 2.25. The answer when you move the load halfway between the 3-foot mark was 0.875. That's 1, 2, 0.875. Oh, thank you, because it wasn't looking real good here. I was just going to kind of fake it in. 1.125. There we go. Looky there. That is the influence line for the bending moment at point B, where this is point B. If you put the unit load here, you cause that much moment over here. If you put the unit load here, it causes that much moment over here. And this height right here was the biggest number we got. That's 2.25 feet. And here's how it's used. Let's just say you have a truck with a 60 kip wheel and a 20 kip wheel. And I'd like to make my life easy here. And they are 6 feet apart. Then I can tell you exactly where you should put the wheels. You should put the big wheel right there. And you should come 6 feet back, 1, 2, 3, 4, 5, 6, and you ought to put the little wheel right there. And the answer for the moment at B, due to the truck, is equal to 60 kips times 2.25 feet. Look at this. Even the units are working out right. Plus 20 kips, 6 feet apart, times the height of that one. I don't remember what that was. 0.75. That is the magnitude of the moment at B. It's the biggest moment that truck could cause. That's just pretty nifty. That's just something I don't think you could ever figure out otherwise. They may say, well, yeah, I would. It wouldn't take me long to realize wherever you're looking for the moment. In other words, if it's your job to design the beam to resist the moment at B, I'd put the big load over where you asked me. And then I'd put the little load on one side or the other. And since on this side the little wheel isn't even on the beam, I'd put it on this side. And then when I give you one like a real truck, the real truck looks like this. There's his front wheel, there's his next wheel, then he's got a wheel there, and then he's got a wheel there, and then good luck, buddy. An influence line will make all the difference in your life. It'll let you get many more things done. Now, the reason I kind of reiterated that what you're doing is you're multiplying a load times the height of an influence line, I've only shown you concentrated loads so far. And a lot of times your loads are concentrated because you've got some trucks, and you also have some uniform because you have the weight of the structure itself and the asphalt and the beams, and they're uniform because they're cars. And when they're cars, we just give up. We don't even pretend we're going to take care of all the little wheels on them little bitty cars. So we just pretend that they are what they call a lane load, and it's a uniform load. Here's how you handle a uniform load. Back to page 1. And now you should, yes, be able to read it. You use a principle from a Mr. Mueller and a Mr. Breslau. And they determined that the influence line, which you are going to be asked to generate on the exam and on the FE exam and after you get out of here, the influence line for any reaction or any internal force, including shear, including moments, it corresponds to the deflected shape of the structure, if you will kink up the structure, if you will bend it, if you'll hurt it, if you'll deflect it. How you are supposed to hurt the structure, bend the structure, permanently deform the structure, to turn it into an influence line is you do the following. You remove the capacity of the structure to carry that force or moment or reaction or whatever, and then you introduce into that structure a unit deformation corresponding to the shear, corresponding to the reaction, corresponding to the moment. Now, the words probably make no sense right now, but it'll take a while. But let me just show you that back on an earlier page, how I'll ever get all this straightened out again. Here is the final results of 30 minutes worth of work to solve for the reaction at A. Here is an influence line. Remind me to send this back out. Here is an influence line. The influence line for the reaction at A will be generated if you will simply take this reaction loose and deform the reaction 1. Look at that. Look at that. When you move this up 1, it turned into its own influence line. And therefore, all you got to do to show me the influence line for the reaction at A is move this reaction up a 1 and draw me what the shape of the structure looks like thereafter. Ooh, all right. There's a structures guy. Here's an influence line for the reaction at B. You simply take the piece of steel, there it is, and you move it up 1. It turns into its own influence line. Now let me show you how you turn one of these things into an influence line for shear. You shear it 1. That's it right there. That is an influence line for anything on earth that has shear in it. You move it up and to the right. Yes, you were permitted to bring this to the exam with you. I will want to make sure you're using yours and not someone else's. Like I said, that's why I asked you to put your name on it. Here is the influence line for shear that you and I generated after about an hour's worth of work. What the devil did we do with it? Here we go, getting close to. Who's got that? Here we go. Here we go. Influence line for the shear at A. Here's all the work we did. Page 29B. Look at all that. Page 29C. Look at all those free bodies. And there was the final answer for the influence line at the middle. Here is what you do. Let me draw. Well, that's okay. You take your beam. I would suggest you take it home. I don't think you want to see, you don't want the boss to see what you're getting ready to do to his beam. You put it on the curb and you run over it and you put a unit kink in the beam. Here is the left reaction. Here is the right reaction. You will notice that your new kinked beam doesn't fit on the supports anymore, and therefore this is a 1. It's a unit kink. You move it down until it fits on the reaction again. Now, the fact that this thing right here doesn't look perfectly vertical, the truth is, when I say deform this thing a 1, I mean just a very tiny one, not big like that. Now, this was 29D, 29A. This was 6 feet, and this was 6 feet. The book says what this is mostly for is so that you can get qualitative magnitudes. In other words, you can see what it looks like. And I can see what it looks like just from that. I can see it goes down to here, goes up to here, and goes down to here. But the truth is, you can get quantitative magnitudes just as easy. And if I were you, I would. He says, once you know what the thing looks like, you're way ahead of the game. Then you only need maybe 1 or 2 numbers rather than drawing 18 free bodies like we did before. You just draw a couple. But my question to you is, if you rolled your influence line generator clockwise from here to here at point A, B, at point C, if you rolled it down, how far did you roll it down? 1 is correct. Then you ought to be able to tell me how far this point right here moves down. In other words, it used to look like this. Point B is 6 feet out of a 12-foot rolling radius. It is halfway out. And so if this rolled down 1, this didn't have much choice but to roll down 0.5. And if this was kinked up to the number 1, and if point B is halfway to the rolling distance where it went down a 1, then point B must have rolled down a half, leaving this at 0.5. And here is your influence line for the shear at A. Now this is so neat and so simple. That's why I told you it's unacceptable to use it on a couple of the homework problems. I want you to suffer. My prof made me suffer. You should suffer a little at least once. You ought to do it by statics. Now, if you think that's nifty, let me show you how you get a moment diagram. This is going to be a zoo. Page 3. I'm trying to find the work we did this morning. There we go. Page 2. Page 3. So I'll call this page 4. I'm going to generate the influence line for a 12-foot long beam at the 9-foot mark. What have we spent? About 40 minutes a while ago getting this. Where'd my influence line generator go? There it is. If you would like the influence line for the reaction at A, there it is. If you'd like the influence line for the reaction at B, there it is. If you would like the influence line for the moment at B, you simply put a unit moment kink in the structure. That is the influence line for all cases. It's only your job is to go put it back on the structure. You take it home and you do this to it. You put a 45-degree kink in there, or you put a 1-to-1 kink in there. Now I'm going to bring it back on the job site. Okay, it looks like that so far. You happy with that? I don't know why you're not happy with that.
How it's supposed to go.
Well, it's not how it's supposed to go. Well, I guess that's okay. It's not pinned on both ends. If a truck drives across it now, you're going to have deaths on your hands. It's your job to bring this point back up to here. Right now, this point is how far below the line? 1? No. 3 is correct. As a matter of fact, it's 3 feet below the line. The reason is it's a unit kink, it's a 1-to-1 kink, and therefore since it's 3 feet from B to C, it's 3 feet from C down to the influence line. So it is incumbent upon you not to roll it about point A and to roll the wrong side and to roll the influence line up until it reaches point C and can be repinned at point C. Now, your beam that you rolled was 12 feet long and rolled up 3. Therefore, this point, since it wasn't as far out, didn't roll up as much. So I'm going to tell you that this point right here is Y. Y is to 9 as 1 is to 12. In other words, because point B is not as far out, it didn't roll up as high. And some people do this. They say Y is equal to 9/12 of the rolling up at the end of the influence line. 9/12 of 3 feet. What did I do wrong over here? Thank you. I don't know why I put a 1 there. We didn't roll it up 1, did we? We rolled it up 3. And that probably is quicker and makes more sense. In other words, if you have something that's going to roll about this point, and you're going to roll that end up 3, then all of these other people are going to go 1/12 as much as you rolled the end, 2/12 as much as you rolled the end, 3/12 as much as you rolled the end, 9/12 as much as you rolled the end. 9/12 of 3 is how big? How many? 2.25. Ooh, I like that answer. Thank you. 2.25 feet. And there's your influence line.
Is it always a 45-degree thing?
Yes. You have to put a unit kink in there to get the numbers. Now, the book, I don't know if he says that, but then the book doesn't really like to use it for numbers. He likes to use it just to get this shape. And then he says, now we know what the shape looks like. Why don't you just go put the unit load here and find the answer there and plot the answer? Well, that works too. It works okay. All right. Now let me see what I got here. No doubt it's here because I haven't left. I've not been from this chair. So we talked about the Mueller-Breslau principle. Now maybe the words make a little more sense. He's saying if you want a reaction, release the reaction, because otherwise the influence line won't move, and move the influence line 1 in the direction of the reaction. If you want a shear, take your influence line and remove the ability for it to take shear. And that's what I just did. And put a unit shear in it. It'll turn into its own influence line. If you want a moment influence line, take the ability for the thing to take moment out in there. It's basically what I did when I yielded all the fibers in the copper. Put a unit distortion in it. And, of course, it's still your job to go put it back on all the supports. And then the resulting shape of that diagram will be the influence line. An amazing principle, and it works. Now then, regarding uniform loads, generally speaking, you will have a uniform load somewhere between maybe, see what you can see here, between, say, points A and B, and you will have an influence diagram. And I'm asking you, if you put the uniform load on this thing, how do you tell how much load it causes? First off, I'm going to tell you that a uniform load spread over a small distance, if the height of the curve is W, and you're going to take an incremental piece of that load, dx, then how much load you are putting on my influence line is dp. I'm also going to tell you that my influence line just so happens to have a height of y at the point where this little tiny piece of load occurs. So I'm going to tell you that dp is equal to height times base for the load. This is the load on the beam. Directly underneath there, I look at the influence line that you generated for me, and it has a height of y, so the chain, or the little piece of force caused in the reaction, or the little bitty shear caused for shear or moment, whatever you're working on, will equal to this force times the height of the influence line. So that says dF is equal to, replace dP with W dx times y. That tells me that you could find the whole force that you caused on my beam, in the beam in shear, on the reaction for reaction, inside the beam for moment, whatever you're looking for, by adding them all up. Adding this little force times this height plus this little force times this height plus this little force times this height. You integrate all the little forces, integral of wy dx. If w is a constant, that's usually the case. Usually most of our loads are uniform loads. If it's not, you're really going to have to do this integral. Then the force is equal to, bring the w outside the integral, is equal to the integral of y dx. Guess who y is? Y is the height of your influence line. Guess who dx is? Dx is the base of your influence line. That's nothing but the area under the influence line. So I can tell you the total shear, or the total moment, or the total whatever caused by a uniform load is, you tell me the magnitude of the uniform load, and you tell me, and you multiply it times the area under your influence line, That'll equal to the total moment, or the total shear, or the total reaction caused. So let's try one. What have I got here? Let's try this. I want the influence line. Seems like I had dimensions on one of these. Here we go. This is the one I started with. Here's a beam. It's a piece of steel. It is 35 feet long. It is supported 10 feet to the right of the free left end and 5 feet from the right end. I would like to know the influence line for the reaction at B. You can do it by statics. I'm going to do it using Mueller-Bress law. Reaction at B. That's it. You finished? I'm finished. This number, this is the influence line for the reaction at B. The reaction at B has moved 1.0. This left end is less than or greater than 1.0. Quite obvious. What's the number? 1.5 is the correct answer. Over here on the right-hand end, it turns out that loads over on that side will cause a negative reaction at B. What is this magnitude? 0.5? Let's see. This is 1. 1 is to 20 as something is to 5. 1 is to 20 as y is to 5. So it's a fourth, isn't it? 0.25. We don't usually put a minus sign on there. You certainly can, but since it's shown below the line, we usually don't bother. Here is a reaction at D influence line. Incidentally, who looks like they're sleeping? Point at him. I'll find out who it is. Nobody? All right. Lane, what is the... Where would you put the big wheel? Lane, got the wrong class here? No, that says 345. What are all those people doing back there that I don't know who they are? Munson, where's Munson? And where's Open North? And who are you? Hunter? Oh, I bet I've got an old one. All right, I'm sorry. Well, all right, let me pick somebody. No, that's okay. That's all right. No, I've got it. I got it somewhere in this mess. Let me pick somebody at random. Hunter? Where would you put the big wheel?
The big what?
The big wheel. That's correct. Point B, Baker? Surprisingly, no. But not a bad guess. And before he answers, I'm going to tell him he's wrong no matter what he says. And because when he says, well, why is that wrong, what am I going to say?
Just for the reaction, isn't it?
It's for the reaction. I'm asking you for the maximum reaction at B. But when he tells me, well, you obviously ought to put the big wheel right here, I'm going to say, no, you should put it here, because I wanted the maximum negative reaction. That is cold, that's right. The question wasn't complete. When I ask you for the maximum reaction at B, you're going to want to know both the positive and negative numbers. For instance, if there's no possibility for this reaction to go negative, you'll build it one way. But if the wheel can get over here and push down and push this thing up, you're going to want to design it as a link. So anyway, the basic answer probably is you put the big wheel where the big influence line value is. And you put the little wheel wherever it goes next to it. Let me just say, if you put the big wheel here and you put the little wheel here, is that what you want to do? It's not, is it? You want the truck to go the other way, where the big wheel is on the span and the little wheel does not reduce that negative tendency, because that'll be happening someday. All right, influence line for the reaction at D. Here's the reaction at D. Here's the influence line. Whoops, I heard something happening there. That's not good. All right, reaction at D. Whoops.
Isn't D under the support?
Are you not happy with that influence line? You're right. Why? Because you were supposed to have it being rotating about this pinned point. Nobody took that pin out of there, thank you. Very good. There's your influence line for the reaction at D. You'll notice it's a straight line. Nobody bent that piece of wire, that influence line generator. This is a 1. This is a 1 point. Y is to 25. As 1 is to 20. So Y is 20 over 25. If you can't do geometry now, you really need to go take that class instead of this one. That wasn't a geometry mistake. Why is it 25 over 20? How would I know I got the wrong number? It was smaller than 1. Okay, good point. So 1.25? And this magnitude right here? Y is to 10 as 1 is to 20, and therefore it's a half. Are you getting ready to catch on fire, or was that your phone? All right. Influence line for the shear at C. C is in the middle of the beam. Here's my influence line generator. Are you ready? No? What do you mean, no? That's not the influence line for shear, is it? That's the influence line for a moment somewhere. That's all right. It's a very good little thing. There's the influence line for the shear. There it is at home. Here it is brought back out on the job. I go out and I stick a steel pin right in there. Next, I see if the truck comes now, he's going to die. So I take this point and I roll it until it gets on the pin, and then I put the second steel pin in there. Wait a minute. I don't have the shear, I don't have the kink at the point I've been asked for. Got to have the kink at the point C. Point C was in the middle. Bingo. Influence line for shear at C. It's a straight line. It's a straight line. Incidentally, you'll notice that when you brought it back from home, this line was parallel to this line. That means that this line must be parallel to this line here. Those two lines must be parallel. When you brought it back from home, it was off by 1.0. You rolled it about this point. This is 10 feet and 10 feet. You rolled this point down 1. This point right here, let me draw the original influence line here. This point was 1. You roll this point down 1. This point rolled down less because it's less far from the point you rolled it about. This point rolled down 10 out of 20 as far, because it's 10 out of 20 as far from the point that you rolled it. 10 over 20 is a half. That means this number right here, it rolled down a half, leaving you at a value 0.5. The whole kink is 1, so this has to be 0.5. And from then on, you can just use similar triangles. It's usually easier. 0.5 is to 10 as y is to 5. 0.5 is to 10, similar triangles, as y is to 5. So y is half of a half. And this one's out here the same amount, 10, and therefore it rolls up the same, 0.5. All right. Let me ask you for this load. I got 2 kip per foot. I'm looking for the maximum shear at point C for this influence line. Let me just redraw it. I'm not going to ask you to do this on a quiz. Because I don't think we've gotten far enough so you can figure that out yet. I just want to show you. All I'm doing is redrawing this influence line. This is 0.5, this is 0.5, this is 0.5, and this is 0.25. Here's the loading. The loading has got a truck and a uniform load. Maybe this uniform load is due to the weight of the deck or something like that. I want the maximum positive shear at C, that's this midpoint here, for this load. This is point A, point B, point C, point D, point E. Where would you put the big wheel? For the maximum positive shear, where would you put the big wheel? At C, to the left or to the right? That is correct. Put big wheel to the right of C. You could also put it at A. And let me change this 10 feet because I wasn't thinking about what structure it was going to go for. Let me make it 8 feet. So you'd put the big wheel here, and you'd put the little wheel here 8 feet away, or you'd put the big wheel here, and you'd put the little wheel 8 feet away. Put little wheel uh, 8 feet away, let's just say, 8 feet away. Where would you put the uniform load? To get the maximum positive shear at C, where would you put the uniform load? Between Charlie and dog is right. And let me say these are little cars that can be broken up. Say small cars. Where else would you put them? And A to D, and A to B, that's right. Between C and D and A to B. In other words, you'd put uniform load here, and you'd put uniform load there. All right. Wake up the guy next to you so he doesn't stay here all night.
Can we bring 3 of these?
You can bring any number of these, but they usually last.
And I was just sitting there bending them for each.
You may bring them pre-bent.
What happens if you put the wheels from B to C?
Then you cause negative shear.
That would just be negative shear.
That's okay. The guy may ask you for negative shear, but then you would also you'd put the big wheel here, and you'd put the little wheel there. Okay. You definitely wouldn't put the big wheel here because you get more shear by putting it here.
But if you put it here, it wouldn't collapse.
It's not going to collapse at all.
Okay.
So that's why we're drawing these influence lines so that you can tell me where to put the loads so that I can cause the worst thing that can possibly happen to me and I can design to resist it.
Okay. Thank you.
Are you saying that for the distributed load, you can split them up, or is
Yeah.
it either location?
Well, it depends really, and we'll get into that next time. If this is for the bridge deck, you've got to put it all the way across because there's no getting rid of any of that weight. But if they're little cars, we can assume that there's a wreck here and a wreck here, and the car's built up and loaded just in this region and left this unloaded. You say, that's not likely. Can you guarantee me it'll never happen? Well, if you can't guarantee me it won't happen, I'm going to make you put the cars here and here, leave them off where it reduces the number, and leave them off where it reduces the number.
So it's just depending on the situation.
Absolutely. Right.
Thanks.
Sure.
When you bent the little wire,
Yeah, that's not a wire. It's an influence line generator. The wire is free.
you bent it up here.
That is correct. In
Could
other
it
words,
not, could it not be the opposite?
No.
way? No.
and the reason is you get the wrong signs.
Okay.
And that's the only reason. You just don't get positive shears. In other words, if you bend it the other way, it'll be upside down. And when the guy asks you for positive shear, you'd load it in the other spans. And in other words,
What makes that way the right way?
well, here's what makes it the right way. You remember when you and I drew a real shear influence line? Well, let's do the moment since I happen to have one here. You remember when you and I drew a real influence line, cut, and this is what it was for positive moment. See how we put positive moment on there? Now let me show you. You're going to be asking, well, why can't you bend it up? Well, if you bend it up, you see, if you bend it this way, then it would bend up and you'd have to roll it down. In other words, this would be your influence line. And you'd have the influence line showing you negative moments are going to be caused when I want those kind of moments to be called positive moments. That's the only reason. All right?
Thanks.
Sure.